length of a curve. We know parametric equations are used when we have curves. If you have 2 points, x1, y1, x2, y2, that would be the distance between the 2 points. That part, what is that distance, that horizontal distance? Louder, okay, louder.
x2 minus x1.
x2 minus x1, okay. And what about that?
y2 minus
y2 minus y1, okay. And if that is A and that is B, what is that? What?
C.
C, okay, what is C?
The square root.
Square root of A squared plus B squared comes from the Pythagorean theorem, C squared equals A squared plus B squared. So what is A and what is B? Well, A is x2 minus x1, and B is y2 minus y1 squared. But that is the distance between 2 points, x1, y1, and x2, y2. Now you see why everything goes back to Pythagoras, from basic distance to angles and complex numbers. All of those are based on the unit circle. Well, all of unit circle Pythagoras. Good with this part? Yes? Okay. How do we extend this to a curve? Something like that. We know it's not a function, but we can quantify that curve using parametric equations if we are able to. You can't always come up with a parametric equation, but when you can, great. Any thoughts on how one can find the length from point A to point B? Yes. Look, prior to that step. Now, what do you mean? What do you mean by integral of all steps, Caitlin?
Just like all the mini functions.
You are correct. I see what you're saying. How about this? What if that part's easy, that part's easy, that probably goes like that. Maybe connected there, 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 there. Right. A bunch of tiny little segments, add them all together, you get the total length, correct? If you do a sum, then it's a Riemann sum. Going back to finite number of rectangles and taking the limit and saying you have infinite number of rectangles, instead of that many segments, if I took infinitely many segments from here to there, add all the distances together, I'm going to get an accurate length. Do you agree? Yes? Okay. But each point from there to there is just the distance for it. Do you agree? Okay. We have to integrate y infinitely many points. That's going back to Riemann sum. Riemann sum, limit n approaches infinity, you end up getting the area under the curve. Same logic, I need an integral. Integral of every single length that I can think of between A and B, infinitely many. But each distance is given by that formula. Agreed? Now, I don't know who you took calculus with, I didn't see any of my Calc 1 students, but why do we call dy by dx, or the derivative of y with respect to x as dy over dx? Why? Of all letters that one can pick, why call it dy over dx? No one knows. Okay, let's go back to middle school, not literally, figuratively. Change in y. Y2 minus y1. You used a notation. Did they use that notation? Change. Slope. Yes, the formula for slope, but the change part, did they use some sort of a notation?
The delta.
The delta, very good. Delta. Change in y is delta y. Change in x, delta x, right? But that change is between 2 points that are far apart. But if they get really close to each other, in other words, infinitesimally small change, then delta becomes big, uppercase, lowercase. Likewise, delta x becomes dx because you are going away from a large distance or distance over an interval to an infinitesimally small distance. Okay, so far so good. What I'm going to do is I'm going to pull dx squared out of the root. If I pull dx squared out of the root, what will I get outside of the root? If this term comes out of the root, what will be
Just,
exactly dx squared or the root of dx squared?
yeah.
The root of dx squared, which is just dx. Good. One there. What about that part? So that's good. That's safe. Well, I took the dx out, so something's got to happen there. Caitlin saves dy squared over dx squared. Do we agree with Caitlin? She gave the correct answer and she doesn't agree with herself. What I did is multiply and divide by dx squared. Yes, and I'm pulling dx squared up. So when I take that out, I get 1. Take that one out, I simply have the denominator term. Good. Okay. Which I can write as square root 1 plus dy over dx squared times dx. That is the distance formula, the length formula. That will work nicely if you have a function, because y is a function, I can find the derivative, but I have something like that, it's not going to work. Yes, because it's a curve, and it will fail the vertical line test at a certain point. So that will not work if we have a curve. For example, the one that we saw, infinity, so then in this case, vertical line test is not going to work. Sure, one might say I can rewrite the function in terms of y. If I recall correctly, the problem that we tried to rewrite last time ended up being cosine of ln of cosine inverse of x? Something along those lines? Or was it sine? One of the problems that we did. Well, something, right? Something like this. We had parametric equations, we rewrote it, and we said, well, why don't we write it as y in terms of x, put it in functional form, and I said finding the derivative here is painful. And we all agreed. If finding the derivative there is painful, take that expression, put it in here, take the square root, try to integrate it to find the length. Would it be painful? Very painful. And, not a good idea. But this came from parametric equations, x, y, represented in terms of t. So if we have a parametric form, if we are able to come up with a parametric form, life is easy. Agreed? Okay. How do we go from here to a parametric version? Well, dy over dx in terms of t or in terms of dt. We wrote it in a certain way. Do we remember? Dy over dx, but dt somehow got to show up. Yeah.
Yeah, I think you end up with dy over dt over dx over dt.
Very good. So dy over dt squared over dx over dt squared times dx. Good. I want a common denominator. What is the common denominator? Because I'm trying to sum that one and that fraction. What is the common denominator? dx.
The teachers can.
Well, then you go back to this one, right?
Yeah.
Yeah, I'm asking, this number, that fraction, how do you combine this?
That by dx over dt squared.
Very good. Dx over dt squared over dx over dt squared plus dy over dt squared over dx over dt squared. Agreed. There is a dx outside, so we'll keep that. I have a common denominator. I can have the numerators. Yes, no, maybe. So dx over dt squared plus dy over dt squared times dx. Erase it. Raise its part. Good. Started with Pythagorean theorem, basic Pythagorean theorem. Distance between 2 points, I got the distance formula. From there, I threw in the derivative and I got a formula. And then I said, well, if you don't have a function and you have a curve, vertical line test multiplier, and even if you try to rewrite a parametric equation, things may not work your way, and you may not be able to integrate things properly. So we will just stick with the parametric form. Why? Whatever you do on the parametric side matches exactly with the functional side. Yes or no? We saw that last night, correct? Whether you find the derivative in terms of dy dt or directly do it with dy over dx, the answer will be the same. Now that we are here, I'm going to pull the denominator out. Yes. Times dx. Denominator comes out of the root, it becomes dx over dt. What do we do at this point? Think of fried chicken. Keep change flips.
What about the square?
Oh, what? Root, it's coming out of the root, right? So flip and multiply, keep change flip, KFC. So dx times dt over dx. What happens to the dx? They get cancelled. Look, I have a nice little formula. And that is how you find the length of a curve, parameterized in terms of length. As I always say, if you understand something, there is no need to memorize. It just comes to you naturally. So that is the formula to find the length of a curve parameterized using the parameter t. We know when you take the derivative of x in a parametric equation with respect to t, you get a function of t, you get a function of t, yes? So that's that. Good.